Welcome to this week's astrobiology seminar. I'm Roger Buick, and it's my pleasure to introduce Giada Arney, Dr. Giada Arney, our very own Dr. Giada Arney. Giada got her bachelor's from University of Colorado in Boulder. She was one of the first dual title PhD astrobiology plus X, in this case astronomy, graduates from University of Washington, where she got her double title degree in 2016. She is now a research scientist at NASA Goddard. Her research interests are pretty wide-ranging. Much of her PhD work was on organic hazes and how they could affect exoplanet spectra. Subsequent to that, she's been pretty actively engaged in LUVOIR development, the large space telescope that would, at least in part, be dedicated to astrobiology. She's also got interested in how atmospheric photochemistry affects exoplanet climate. And her most recent enthusiasm seems to be what she's going to be talking about today, which is she's got fascinated by Venus, perhaps under the evil influence of her PhD advisor, Vicky Meadows, who at least started off being a Venus astronomer. So Giada's going to talk to us today about Venus, the exoplanet in our backyard. Venus being a mystery to everyone because of its cloud cover. But Giada's going to try and lead us through that. So, Giada, thank you very much for coming to us so late in your evening, and please take it away.
Thanks, Roger. Yeah, I'm sorry I can't actually be in Seattle. Vicky told me it's a very nice, unseasonably sunny day there, so I feel like I'm doubly missing out. So I'm going to talk about Venus, the nearest planet in our universe to us, as a sort of example of a planet that I think has big picture connections that reach both across space and time and will help us to address some very large topics that really lie at the heart of what we mean when we ask ourselves, where can we find habitable worlds elsewhere in our universe? And these are questions and connections that reach not just across our solar system, but also to other solar systems, because they're about general processes and phenomena that might play out on countless worlds in our universe. And I always like to show this video. So this was made by some of the graphics folks at Goddard, and I just think it's cool, showing the different planets of our solar system. So here's an artistic depiction of current Venus. Venus is a very dramatic and complicated and interesting planet. This is a world whose surface temperature is hot enough to melt lead at a scorching 740 degrees Kelvin on the plains. And that's thanks to its crushing 93 bar atmosphere, composed mostly of carbon dioxide, which is a potent greenhouse gas. It has these beautiful, dense, butter-colored clouds, but those clouds are not made of water. They're made out of a concentrated solution of sulfuric acid and water. They're about 75% sulfuric acid. And those clouds also contribute to the scorching greenhouse effect. So this is really not a pleasant environment to be in. It's an environment that's extremely desiccated, extremely acidic. It's just not a nice place that you'd want to be. But it might not always have been that way. So now let's just imagine what Venus may have been like billions of years ago. What I've always have found the most compelling thing about Venus is the fact that there's this tantalizing hints suggesting that this world may once have been habitable with an ocean of water on its surface. So here's a new artistic depiction of what that past phase of Venus's history might have looked like if this story is true, if Venus did indeed have oceans. Now, the usual story goes that if Venus had oceans and it lost those oceans over time, Our sun gets about 6% more luminous every billion years as part of normal stellar evolution processes. And so eventually, under the forcing of that brightening sun, if Venus did have oceans, it would have no longer been able to support those clement and stable surface temperatures. The oceans would have massively evaporated into the planet's atmosphere, which, because water is a greenhouse gas, that would have further warmed the planet, evaporating more water into the atmosphere in a runaway process, driving up the temperature until your atmosphere is so hot you're not able to condense the water into clouds. You've got water vapor all the way up through the atmospheric column and water vapor hanging out near the edge of space. Now, when you have water vapor very high up in the atmospheric column, when UV light hits those water molecules, it can break them up or photolize them. And when you do that, you'll get free hydrogen. And for a planet the size of Venus, it's very challenging to hold on to a small lightweight molecule like hydrogen. And so those will be easily lost to space. The key central evidence that people point to when they talk about past water loss on Venus as evidence for that water is what's called the D to H ratio, or the deuterium to hydrogen ratio on Venus. So when you lose your hydrogen to space, that gets very easily lost because it's lightweight. If you photolize heavy water, or HDO, the heavier deuterium will be a little bit more challenging for the planet to lose. And so a little bit more of it will stick around. So you will preferentially enhance your D to H ratio through water loss if Venus did indeed lose a lot of water in the past. And so what we see on Venus is it's got a high D to H ratio compared to Earth, about 120 times that of Earth. And if we assume that Venus and Earth formed from the same material, they should have started with the same D to H ratio. And so we have to explain that high D to H ratio on Venus. Water loss is one way to do it. There are other ways to do it involving things like volcanic processes, impact processes. To tell the difference between these processes and really understand which one is correct, or perhaps there's a combination of things that are correct, we really need more data from Venus, because this is a world we just don't understand very well. And if Venus was truly habitable, the dramatic story that we're going to uncover is a story about the life and death of habitability, where the current state of Venus is basically the planet that was alive is now dead and not habitable, at least not habitable in terms of the way we think about habitability traditionally. So the current state of Venus really represents the last pages of a very long and complicated history that we don't understand. Unfortunately, most of that history has been lost. Most of the surface of Venus is about the same age. It's about 500 million years old. That's thought to be because Venus may have been catastrophically resurfaced about 500 million years ago. So if you want to look for geological remnants of the past history of Venus, that might be quite challenging, although as I'll mention later on in this talk, there may be parts of Venus's surface that might be older, but the fragments that are left behind, there's these tantalizing clues in the atmosphere and on the surface, and we would love to better understand them so that we can better understand this very dramatic and complicated story. And this is a story that's also relevant to Earth. So as our sun continues to brighten with time, the story of the life and death of habitability is eventually going to happen here too. So eventually, Earth might look more like Venus than it does like Earth today, as the sun continues to brighten with time. Eric Wolf and Brian Toon used a climate model, and they predicted that the conditions you need to pop Earth into a Venus-like state with a runaway greenhouse occurring will be met about 2 billion years into Earth's future. Now, I like to think of that 2 billion years as a sort of upper limit to the amount of time Earth can remain habitable, because there are other processes that might cause Earth to lose habitability before then, like, say, the cooling of Earth's interior and the shutdown of plate tectonics. But no matter the mechanism, it is certainly, I think, sobering to think about Earth looking like Venus does in the future. And so by studying Venus, we can, in a way, study a possible future of Earth. But now turning back to Venus, I think, the question of whether Venus was ever habitable is one very important question we haven't yet fully addressed really at all. But there's another important question, which is how Venus could have been habitable if it was. And this is a question that I'm really interested in as someone who studies exoplanets, because the answer to this question really sort of pushes on the boundaries of the habitable zone. So here you're looking at the habitable zone, which is the region around stars at different temperatures where you can support liquid water on a planet's surface. And so the habitable zone is that blue river that's running down the center of this plot. The key thing about this particular habitable zone that I'm showing you here, though, is that this is a special habitable zone. This is the zero-age habitable zone. Remember, I told you before that stars get brighter over time. And so the boundaries of the habitable zone will move outward away from the star over time as the star is getting brighter. But this particular habitable zone here is the habitable zone for our solar system when the sun was, well, for all of these stars, when they're 0 years old. So when they're baby newborn stars. Now notice something interesting, which is that in this version of the habitable zone, Venus is not in it, even when our solar system first formed, and the habitable zone boundaries were as close to the sun as they were going to get. Now, an important thing to keep in mind, though, is that this habitable zone that I'm showing you is something called the conservative habitable zone. The conservative habitable zone is the habitable zone that we calculate with our climate models when we're using simplistic models that don't include more complicated planetary feedbacks that you might need, say, a 3D model in order to simulate. These feedbacks include things like, say, cloud cooling feedbacks that I'm going to talk about in just a moment. These kinds of feedbacks can extend the boundaries of the habitable zone beyond these conservative limits. But I still think the conservative habitable zone is useful, even if it doesn't encompass all of the parameter space in our universe where planets can be habitable, because it defines the part of parameter space that any space telescope that's looking for habitable exoplanets must be able to access, because it's the place in parameter space where you might imagine sort of maximizing your chance of finding habitable planets. But still, it might not show us where all of the habitable planets might be. Now, an interesting property of Venus that turns out to be possibly relevant to enabling its early habitability is one of its unusual properties, which is the fact that Venus rotates very, very slowly. It rotates not just slowly, it's actually super weird because it also rotates backwards compared to the other planets. And it turns out that recent 3D climate modeling efforts have suggested that this might be relevant to enabling habitability on early Venus, interior to the inner edge of the conservative habitable zone. So what you're looking at here is a plot from a study by Mike Way from 2016. This is a plot of cloudiness on Venus 2.9 billion years ago. And these clouds here that you're looking at are water clouds. They're not sulfuric acid clouds. Mike wanted to understand how you might be able to enable habitable surface temperatures on Venus billions of years ago through cloud feedbacks. And his paper talks about how Venus's slow rotation rate might be linked to its possible early habitability through cloud feedbacks. So just to orient you, what you're looking at on this plot, if you're not used to looking at plots like this, is the center of this plot shows noon at the planet's equator, and then the edges of the plot show midnight on the planet's night side. And then the north and south poles are at the top and bottom. So basically imagine, you know, unfolding Venus and laying Venus flat so that you can see both the day side and the night side at once. And that's what you're looking at on this plot. The color scale is the percentage of cloudiness on the planet. And notice how the clouds are intensely concentrated in the center of this image, and that is on the planet's day side. What Mike found in his models is that when you have a very, very slowly rotating planet like Venus, you can drive extremely high levels of cloudiness at the subsolar point, so the point directly below the sun. The reason is because slowly rotating planets have weak Coriolis forces and very long daytime illumination at one point. And so that will promote strong convergence and convection in that substellar region where you can form large amounts of cloud. This is similar to the high cloudiness that we see on Earth in the intertropical convergence zone, except for early Venus. If early Venus did indeed rotate as slowly as it does today, the sun would be sitting at more or less the same point above the planet's surface for a much longer period of time than it does on any point on Earth. And so it can be overcast on one given area for a very, very long time, for months at a time. So you've got this huge, bright, reflective cloud deck on the day side of the planet, driven by this slow rotation that gets concentrated on the day side of the planet. And of course, these clouds are very reflective, or they have a high albedo. And so if you have a high albedo, that's going to lower your temperature by reflecting a lot of incoming light back to space. Now, there have been other studies, such as one by Mark Bullock and Dave Grinspoon, that have suggested that cloud cover could help to maintain prolonged moderate surface temperatures on Venus. What I think is really cool about Mike Way's study is that he was actually able to link this needed level of high amount of cloudiness to a different planetary property, that is Venus's rotation rate. And they find in a more recent study by Mike Way and Tony Del Genio that you don't need that much water to drive these feedbacks. You can do it with about 10 meters of water equivalent to drive these cloud albedo feedbacks. And I should note, the type of atmosphere that they're assuming in these simulations is not the atmosphere of modern Venus. This is a past, hypothetical habitable Venus. So the atmosphere they're assuming and the composition of the atmosphere is Earth-like in composition for these habitable simulations. It's not, take Venus as it is today and inject water clouds and see what happens. You're not going to take Venus today and turn it habitable, but you can take an assumed, potentially habitable environment and maintain habitability over time with these kind of feedbacks. Here's a temperature map that corresponds to those simulations, showing the surface air temperature. And you can see that it's habitable, it's moderate in temperature. And what I think is really cool about some of their simulations is that it's actually cold enough on the night side of the planet for it to snow, which is, I don't know, I always like to bring that up because I think it's so evocative to think about Venus, snowfall on Venus on the night side compared to the current state of this planet. But there's a really critical caveat here, which is the fact that we don't know if Venus's slow rotation rate is primordial. We don't know if it rotated as slowly in the past as it does today. And in fact, there's reasons to believe that it didn't and it rotated faster in the past. If we assume, or if we interpret its current slow rotation rate to be the slowing of Venus's rotation due to the impact of tidal forces on Venus's thick atmosphere over time, and that thick atmosphere is a symptom of its loss of habitability. But if Venus was rotating slower, but maybe not quite as slow in the past, you still might be able to drive these feedbacks. So they find that if it was rotating at least 16 times slower than Earth does today, that would be sufficient to enable moderate surface temperatures. Now, this is still a problem because we don't know what Venus's rotation rate was like in the past. But I do think it is interesting to consider this, as a process that can enable habitability on planets, not just within our solar system, but also beyond the solar system. And there's another interesting thing that has arisen from these studies. So I talked about how traditional thinking has attributed the loss of water on Venus to the influence of the brightening sun. But Mike Way and Tony Del Genio's more recent paper from 2020 suggested that given the cooling cloud feedbacks that I just described, if Venus rotated slowly, throughout geological time, given that plus a carbonate silicate feedback cycle, so that's a cycle that recycles CO2 in our atmosphere back into the mantle, back into the atmosphere. It's a cycle that stabilizes the climate on Earth over geological timescales. Given both of those, it is possible that Venus could have maintained habitable conditions all the way to the present day of our solar system, which is, again, a mind-blowing fact if that's true, because that has implications for the distribution of potentially habitable environments beyond our solar system. So what they suggest that if, this is still a really big if Venus was habitable in the past, enabled by these cooling cloud feedbacks, together with a CO2 recycling carbonate silicate cycle, you would need something else to cause Venus's loss of habitability. And so they propose it might be massive outgassing of greenhouse gases associated with massive production of magmas, perhaps analogous to the formation of the large igneous provinces on Earth. So what they propose, and that's what you're seeing on this plot here, is a very long temperate period stretching all the way to 700 million years ago, which is very, very recent in the history of our solar system. And that 700 million year age was chosen because that's the age of widespread flood basalt plains on Venus, which, perhaps might have been the massive outgassing event that they suggest you might need if these other things were in place to enable habitability on early Venus. But again, massive caveat, we don't know if any of this is true. There's a lot of different stories that we can tell that are consistent with past Venus. Habitable past Venus is just one of those stories. The current state of Venus is also consistent with not habitable in the past. So we certainly need more data to help tell these different stories apart. Now, I like to think of early Earth as a good way to broaden our perspective of what we might be looking for when we search for potentially habitable exoplanets. Because early Earth was habitable and inhabited, but it looked very different compared to the way Earth does today. But this is also true for Venus, and it is, there's this tantalizing possibility that Venus may have had this extended habitable period for a very long amount of time. If only we knew that were true. And if it was true, I really think that it's an important finding because it does suggest that habitability might be more tenacious, even in the face of these forces that might, otherwise cause the planet to not be habitable or lose habitability, like the amount of solar energy that Venus receives from the sun. But again, I think we're getting a little bit ahead of ourselves because we don't yet know whether Venus was ever actually habitable. Like I was saying, we can piece together this story that is, consistent with past habitability, but there are also stories that people can piece together that are consistent with Venus never having been habitable. And so really, we do need more data to help us understand this, this dramatic story that we would love to understand better. We would love to know better what the atmospheric composition is. We'd like to better measure the D to H ratio so that we can use that as input to our models to help us understand the timing and quantity of water that was lost on Venus. We'd love to better understand atmospheric loss rates that are relevant to the loss of water on Venus's atmosphere. We would love to better know the noble gases that are in Venus's atmosphere. Noble gases are non-reactive, and so they can record a long history of processes on a planet over time. And there may be clues on the surface too, as I alluded to briefly earlier. So although most of Venus's surface is interpreted to be about the same age, and that is interpreted by some scientists to be due to catastrophic resurfacing of the entire surface of Venus, although there are other competing hypotheses to explain that. But there might be older regions of Venus, and those are being indicated here on this slide with the white blinking outline. They're called tessera regions. These tessera are highly deformed highland regions, and it's possible that they are older than the surrounding terrain. And if that's true, they may record a more ancient history of geology on Venus that predates that catastrophic resurfacing event. What's really tantalizing is that based on emissivity measurements, these emissivity measurements are consistent with the idea of these tessera, at least some of them having a more felsic composition compared to the surrounding terrain. Felsic rocks are interesting because at least on Earth, they form from continent building processes. And so if there are widespread felsic rocks on Venus, it's really hard to imagine how they would have gotten there without plate tectonics in Venus's past. And plate tectonics, at least as we know it, needs liquid water. And so that would point to this past habitable phase of Venus's history. Now, understanding the story that I'm describing to you is even more important when we consider exoplanets, because habitability is the outcome of a very, very complicated web of processes. And so this figure here is from Vicki Meadows and Rory Barnes' review article about factors that affect planetary habitability. Vicki always, when I was a grad student, she liked to call this the planets are hard diagram, because it really does show that planets are hard to understand. There's so many different complicated and interrelated phenomena and processes that go into making a planet what it is. And during this talk, I've already mentioned a few of these processes, either implicitly or explicitly, and that's not even half of all of the processes that are relevant to habitability, because it is such a complicated thing. And we don't yet know if Venus was ever habitable in the past, so consider that. And consider that what we know from Venus and what we will know from Venus in the future is so much more detailed than what we will ever know from any individual exoplanet. And so you might wonder, is there any hope of really truly understanding these exoplanets as complicated worlds and understanding this data limited and noisy spectra that we're going to be obtaining from exoplanets in the future when we can't even understand the history of Venus right next door to us? And I think there is hope, even though exoplanets will be challenging to interpret. We can really tackle the problem by using theoretical modeling to understand the kinds of challenges that we're going to face. So here are some simulated spectra of the exoplanets in the TRAPPIST-1 system, which is a system of 7 planets. It's about 40 light years away. And people love this system because it's got these 7 terrestrial planets. Some are inside the habitable zone, some are interior to the habitable zone, some are exterior to the habitable zone. And this is a very observable system to the upcoming James Webb Space Telescope. And this is a figure from another former UW grads paper, Andrew Lankowski, showing what these different TRAPPIST-1 planets might look like if they were Venus analogs. In the top panel, it shows what their spectra look like for clear sky planets. And in the bottom panel, it shows what they might look like when you put realistic Venus-like clouds into the atmospheres of those planets. And the important thing to notice is that the spectra, at least of some of those planets, dramatically change when you add clouds, especially for the hotter planets with clouds. And that's because for these hotter planets, the clouds cannot condense deeply down into the atmosphere. They can only condense high up in the atmosphere. So you get these high altitude cloud decks, and those high altitude cloud decks can strongly dampen your spectral features. Because if you can only see above the clouds, if the clouds are opaque to you at these wavelengths, that means that you'll only be able to sample the atmosphere above the cloud deck, and that atmosphere might be rather rarefied. And so the spectral features of the gases might be suppressed in strength compared to the clear sky planets. Joanna Barstow, she also, so there's been a number of papers, like I could list a zillion papers that have talked about how clouds make things complicated for observing exoplanets. But I like this quote from this paper by Giada Arney, where she says, the cloudiness of a Venus-like atmosphere would inhibit our ability to draw firm conclusions about the atmospheric composition, making any result ambiguous, which is, that's pretty damning. There's nothing ambiguous about what she's saying there. She's saying clouds will make things hard. And I think it gets even more complicated when we consider the fact that high altitude clouds in a spectrum can actually mimic the spectral appearance of a very different kind of planet with a very different kind of atmosphere. That is a thin, clear sky atmosphere, an atmosphere with a very low altitude cloud deck. So this is a plot from another former UW grad, Jacob Lustig-Jaeger. What Jake is showing here on this plot is he's showing, again, the planets of the TRAPPIST-1 system. That's what each of those little circles corresponds to, as they correspond to a different planet. The top sort of track of planets is for, again, planets with clear atmospheres, and the bottom track is for planets with cloudy atmospheres. He's showing the maximum pressure on the y-axis that you can see in these planets' atmospheres when you observe them in transit transmission, which is the technique that James Webb is going to use to observe exoplanets. So you're basically observing the planet being backlit by its star, and you can see the transparent part of the atmosphere above the cloud deck, but you can't see into or below the cloud deck. And when you have these high altitude clouds, well, you're going to be only probing the rarefied atmosphere above the clouds, as I mentioned before. So notice for the cloudy planets, as you go closer to the star, so as you decrease the semi-major axis, which is the planet-star separation distance, you're probing to thinner and thinner amounts of atmosphere above the cloud, right? That makes sense. The atmosphere is getting hotter, so the clouds are lifting to higher altitudes. But what's interesting that Jake points out in his paper is that this could actually mimic what you might expect to see if you're seeing a trend of, actually thinner atmospheres as you get closer to the star. Many of the stars that the James Webb Space Telescope will be observing are very active stars. So for these very, very active stars that flare and produce tons and tons of high energy radiation, you would expect that they might be stripping away their planetary companions' atmospheres to space, especially for planets that are closer to the stars. And so if you see a trend of thinner and thinner atmospheric pressures as you get closer and closer to the star, there's an ambiguity here of what you might be seeing. Are you seeing atmospheres that are truly thinner, which is, something that this plot is showing? It's showing that you're seeing lower and lower pressures as you get closer to the star. Or is it something very different? Is it planets with thick Venus-like atmospheres where you have the clouds lifting to higher and higher altitudes, so you can only probe thinner and thinner atmospheres above the clouds? Those are very different phenomena. So there's an interesting degeneracy here of how we might interpret this effect. So clearly, exo-Venus planets may be difficult to interpret for a number of reasons. It's going to be really, it's going to be difficult to interpret the spectra of any exoplanet, given just given the fact that they're many light years away from our solar system. But I think for these cloudy planets, the challenges are just sort of exacerbated. But I do think there is hope, because we can make the models that we're going to use to study and understand and interpret exoplanet observations better by anchoring them in robust data from our solar system. So by using data from our solar system, we can improve and we can validate those models so that we have confidence that when we apply those models to exoplanets, we know that they're producing physically valid results. So for example, one of the things Jake suggests in his paper that we might do to sort of break that degeneracy I was talking about is you might compare statistical population and insolation trends in cloud behavior to the behavior you predict from models. And those models, of course, we need to constrain them with the data that we measure in our solar system. So that might help us to understand what we might see if we see trends like what I just described. And it goes the other way too, because even though exoplanets are relatively data limited compared to the worlds of our solar system, there are many of them. We now know of thousands of exoplanets, and there are countless more that we have yet to discover. And so they can inform us of planetary statistics on a scale much larger than we can understand in our own solar system. And they can also reveal types of worlds that we don't have in our solar system. Worlds like hot Jupiters, which are Jupiters that are orbiting very, screamingly close to their stars, or mini Neptunes or super Earths, or undoubtedly countless other worlds that we can't yet imagine because we haven't yet discovered them. And another key thing about exoplanets is that even though we can't get into a time machine and go back to our solar system's past, by looking to the exoplanets, I think we can get the next best thing, because we're going to be able to observe planets at different ages and stages of evolution. And so they might show us examples of planets that might be analogous to past phases of planets in our solar systems and their histories. So, for example, wouldn't it be nice if we could observe slowly rotating exoplanets and see that they're generating thick clouds on their day side that's cooling their surface temperatures down enough so that you can enable habitability on planets interior to the traditional inner edge of the habitable zone? Doesn't that sound familiar? And in fact, we do anticipate observing many slowly rotating exoplanets around the low mass stars that the James Webb Space Telescope is most able to access. The reason is because when you have a low mass star, which is the kinds of stars the James Webb is going to be able to observe exoplanets around, it's also a low luminosity star. When you have this little tiny low luminosity campfire that your planets are orbiting around, they're going to have to huddle up very, very close to that stellar campfire in order to stay warm. So your habitable zone will be very, physically close to the star, and also interior to the habitable zone will be very physically close to the star. So planets orbiting in and interior to that very low mass star's habitable zone will be vulnerable to the influence of stellar tidal forces. And those stellar tidal forces can slow the planet's rotation rate down until the planet's rotation rate, so that the amount of time it takes to spin on its axis, matches its orbital period, which in some cases might be slow enough to trigger these feedbacks, these cloud feedbacks that I was describing. And this circularization is the same reason why the moon always has one face to Earth. Tidal forces from Earth on the moon slow the moon's rotation rate down until it spins on its axis once every time it goes around the Earth. So it's the same process that we anticipate is occurring on many of these exoplanets. Now, having other planets in the system and their gravitational forces can complicate things, but we do anticipate that many of the planets we observe will be in a different rotation regime compared to the planets that we know and love in our solar system. And And so these very same feedbacks that could have enabled habitability on early Venus have been studied in the context of these slowly rotating exoplanets. In fact, these studies that investigated these cloud feedbacks on these slowly rotating exoplanets actually came first. And then this process was applied to Venus. So I think that's a really wonderful example of synergistic exoplanet and solar system science. And it's really important to think about Venus-like exoplanets and planets that are at Venus-like orbits, because the James Webb Space Telescope is biased towards detecting those kinds of planets. So I told you the James Webb Space Telescope is biased towards detecting planets around low mass stars, but it's also biased towards detecting planets that are close to their stars. So this is Stephen Kane's Venus zone, which shows the region around stars at different temperatures, where we might expect to find Venus analog exoplanets. But it's complicated, right? Because there might be Earths in the Venus zone. We already, we suspect that there might be these feedbacks in place that can enable habitability interior to the traditional inner edge of the habitable zone boundary. And so the habitable zone boundary might be fuzzy. And it gets even more complicated, actually, because it's been suggested that early stellar evolution processes for these low mass stars that James Webb will be able to observe could actually form Venuses in the habitable zone. And that's the region where you should be able to, have habitable Earth-like planets, but you might have these Venus imposters lurking among them. The reason why has to do with the way stars evolve and really how they evolve early in their history. So this is just a pretty picture of a star forming region, but there's a period that stars go through when they're not even born as proper stars, called the super-luminous pre-main sequence phase. And that's a period when the protostar is contracting down until it gets dense and hot enough to actually ignite hydrogen fusion in its core. When that hydrogen fusion ignites, then it turns on as a proper star, and it's on what's called the stellar main sequence. But before that, when it's contracting down into becoming a proper star, it's very, very luminous. The reason why is because it has a very large surface area, right? It's a very large volume thing that's contracting down. And so it emits a lot of radiation from that very large surface area. This luminosity is very, very high. And that's interesting because the superluminous pre-main sequence phase lasts a lot longer for low mass stars, like the stars that James Webb will observe, compared to more massive stars like the sun. So this is a plot from another UW grad. I'm trying to highlight UW grads here. This is Rodrigo Lugar and Roy Barnes. So this is showing the position of the inner edge of the habitable zone on the y-axis there as a function of time, which is on the x-axis, and you can see the approximate planet formation timescale indicated there. So the sun is on the top. The lowest mass type of star, which is an M8 star, TRAPPIST-1 is an M8 star, is on the bottom. Those are just stellar classifications. The superluminous pre-main sequence phase is this period here, and that I'm showing you for the sun and for the M8 star. So it's that phase before the luminosity levels out. When the luminosity levels out, that's when hydrogen burning turns on. That's the main sequence. But prior to that, we're in this superluminous phase. You can see that for the lower mass stars, this phase lasts a lot longer compared to higher mass stars. In fact, for an M8 star, it can last for up to 1 billion years. So if you have planets that form and are orbiting in what are ultimately the habitable zone boundaries, they might spend up to 1 billion years receiving much higher levels of stellar energy compared to what they will ultimately receive once the star settles down and properly turns on. So these poor baby planets might have all their water and their volatiles driven off before their star properly turns on, and they might turn into Venuses before their star ever really forms, ever finishes forming into a star. So the habitable zone is clearly complicated, and I think it's especially complicated for these unruly low mass stars that have these interesting feedbacks. So Venus is telling us that, the habitable zone is complicated, but the habitable zone is still very, very useful because it does still give us a search space of where to start searching. And I think it's also important to remember that the habitable zone boundaries are a testable hypothesis. So when we actually start to get data from exoplanetary systems, we can measure, we will see which planets are habitable, which ones are not, and how they're distributed. And I think that will be really interesting once we actually can start to make those measurements. Okay, so shifting gears just a little bit, but sticking with exoplanets. Venus may also be able to teach us about oxygen as a biosignature. So biosignatures are remotely observable signs of life. O2 is arguably the most, well, not even arguably, I don't think anybody is arguing. O2 is the most important biosignature for Earth, certainly for modern Earth anyway. There are false positive processes that can form biosignatures abiotically, however, without the involvement of biology. Rodrigo Luger and Rory Barnes pointed out that when you have these post-runaway exoplanets that undergo extreme water loss, you might get left behind with an oxygen-rich atmosphere, because your hydrogen, right, at the top of the atmosphere is being lost to space, but there's a question of what happens to the oxygen. If your oxygen is sticking around, being left behind in the atmosphere, they calculate that depending on the initial inventory of water that you lose, you could generate an atmosphere of tens to hundreds to even thousands of bars of O2, depending how much water is lost. Now, of course, on Venus, if Venus did lose a lot of water in the past, it clearly does not have an oxygen-rich atmosphere today. So if Venus lost a lot of water in the past, we lost the hydrogen to space, but where did the oxygen go? Well, some of that oxygen may have reacted with the surface and been lost to reactions with the surface rocks. But some of it may have actually been lost at the top of the atmosphere, just like the hydrogen. So this is from a talk that I saw just this morning by Shannon Curry, and she gave me permission to put this slide in this presentation. So thank you, Shannon. I thought it was really interesting. So what you're looking at here is oxygen lost at Venus today. The top panel of this plot shows the sunspot number on the sun. So the reason why that's important is because the activity level of our sun tracks with the sunspot number. So when there's higher numbers of sunspots, the sun is generally more active. When there's lower numbers of sunspots, the sun is generally less active. So you might expect that atmospheric loss on Venus might, scale with that. But the important thing to look at here is the bottom plot, which shows oxygen ions being lost at the top of Venus's atmosphere. So today on Venus, we're losing, 10 to the 24 to 10 to the 27 oxygen ions per second. And those numbers don't mean anything to me. But what does mean something to me is the right axis on the bottom, which is how those different fluxes translate into meters of water that those oxygen loss fluxes would correspond to, integrated over all of geological time. And there's a wide range here which is not very satisfying, 0.0093 all the way to up to 9.3. So a couple things that are important is these are, instantaneous measurements of the flux of oxygen being lost on Venus today. That doesn't mean that they are, that the oxygen loss rate in the past was always that. But what is, I think, interesting and important to keep in mind is that the sun was more active in the past. We think the sun was perhaps a lot more active in the past because the sun rotated more quickly in the past. So that would mean that more O2 would have been lost from Venus's atmosphere in the past, which would mean that the amount of water Venus could have lost, given this scaling relation, would actually be higher than the amounts that are shown here. In Shannon's words, as she said this morning, these meters of water lost are probably massive underestimates. So I think that's pretty interesting. And the reason why you can lose O plus ions at the top of Venus's atmosphere is because these charged ions can actually be driven away on electric field lines, which is pretty interesting. And there's actually oxygen, not as in O plus, but actually as in O2, like the oxygen we're breathing in Venus's atmosphere right now in trace amounts. We know this because it's being formed from CO2 photolysis on Venus's day side, and that free oxygen then recombines as excited oxygen on Venus's night side, which we see evidence of in the form of air glow, this beautiful spatially and temporally variable air glow that we can observe at 1.27 microns on Venus's night side. Even though we see evidence of excited oxygen on Venus through this air glow, however, the abundance of ground state oxygen on Venus is highly, highly uncertain. And so it's thought that that may be due to very, very rapid removal of that O2 from the atmosphere, possibly due to something like catalytic chlorine chemistry occurring in Venus's atmosphere. And I know Vicky's current postdoc, Mike Wong, has been working on this with photochemical models. What's interesting and important about this is that these processes that are forming O2 on Venus today and also removing this photochemical O2 on Venus today might be relevant to thinking about processes that can both form and also scrub out abiotic false positive O2 in exoplanet atmospheres. And the importance of Venus in the context of understanding biosignatures was articulated in the 2018 Astrobiology Science Strategy report, where they talk about how Venus is so important for understanding the likelihood of false positive biosignatures on exoplanets. So in general, Venus is a very, I think, compelling and dramatic and dynamic world. And it's a planet that can help us to understand questions that really lie at the heart of what it means to be a habitable planet. And as we search beyond our solar system for potentially habitable worlds elsewhere, we should remember that right next door to Earth, there is a planet that may have once been habitable right next door to us. And that might be Mars, but it certainly also might be Venus. And so by studying the evolution of a world like Venus, I think that can tell us a lot about the states of exoplanets that we might observe in the future. And just to throw another quote up, this one is from the 2018 Exoplanet Science Strategy report. I like this quote. It says, ultimately, the assessment of whether or not a planet is habitable will need to be embedded in the context of the outcomes of terrestrial exoplanet evolution. And so in order to understand those outcomes, in order to understand this evolutionary process, what better laboratory to do that than these worlds we have right here in our own solar system that we can actually get, detailed data from. So Venus is waiting for us, and it would be wonderful to get more information from this planet. So that's the entirety of my talk. And if there's time, I'm happy to take questions now.
If anyone has a question for Giada, you could either enter it into the chat room or jump in and ask her. I can't see all 90 participants in this talk, so you'll have to make yourself aware to Giada that you've got a question.
Hello, Giada, it's Dave.
Dave.
You always have a ringer in the audience. The work by Way and Delgenio is intriguing, and it's a great new way of looking at a great new approach for looking at Venus, and it opens up a lot of interesting doors. But it seems a little bit like you need a whole lot of really great things falling your way to really make this work. You mentioned a couple of possible observables, but you didn't go into them in very much detail. First of all, what would you look for to determine whether or not Venus has been, let's say, rotating at its current rate for 4 billion years versus something a little bit more like what we had been thinking, which was it was being tidally slowed down by its interactions with Earth primarily, and that would have taken maybe a good fraction of 4 billion years to happen. So you have that kind of a thing to look for. And then the other kind of thing to look for is maybe looking for the tessera and looking for a lot of felsic material on the surface would be a fascinating way to do this. But what do you need to find specifically? How much of it? How deep? Do you need a seismometer on the surface to tell you something about, a felsic covering is different than, let's say, a lot of, a continent made of this stuff.
Yeah, well, as always, Dave, you have excellent questions. The question about the rotation rate, I actually don't know the answer to that. And if someone in the audience knows the answer to that, I'd love to hear the answer to that question.
Once again, remnant magnetic fields might be an approach to look for something like that.
Okay.
Venus spent a large fraction of its life spinning fairly fast. Why, it might have had a dynamo, and if not, why not? And if it had a dynamo, it would have had it would have produced some kind of magnetic signature that we might be able to look for in some way with some kind of vehicle orbiting maybe a little closer in than we've gone, or maybe balloons or something, but something like that. I'm really grasping at straws here.
Yeah,
because
no, I mean, that makes sense, at least to first order.
Yeah.
Yeah, the question about felsic rocks. So I've had this question as well, is how much felsic rocks do you need to be confident that what you're detecting is, truly the remnants of past plate tectonics? And I've had it explained to me, my proper geologist, I'm not a geologist, that if you had widespread amounts of felsic rocks, and I guess I don't know how to quantify what widespread is, but I'm certain that folks have in the literature, you can form a little bit of felsic rocks without continent building processes through just water in the mantle. But to have lots of felsic rocks, if it is truly the case that you have large, zones of felsic rocks on these tessera, it is my understanding, according to what I've been told by proper geologists, you can't do that without a process like plate tectonics. So the size demarcation between, tiny regions to big regions is out of my wheelhouse. But certainly, as I understand it, if we see wide regions of felsic rocks, that would be very, very interesting, because you can't form that without a process like plate tectonics. You can form small amounts without plate tectonics, though. Yeah. So that is critical.
I think the third dimension will be the critical one here, not really just the aerial coverage of felsic rock, but if we find some, I think the real challenge will be finding a way to figure out whether we've got something that's really vertically extended as well. How much mass am I really talking about here? Is it just we already know that the high altitude regions on Venus are covered with a low emissivity material at radio wavelengths that we don't know about. You can imagine other kind of superficial coverings that maybe don't go more than a few centimeters deep, and that probably wouldn't be a strong evidence for a long-lived kind of active region. I think we also need to have another conversation with our geologic colleagues, our geology colleagues, on the time scales and just getting a better understanding of the formation of this kind of rigid lid kind of structure we have to Venus, and how would we go about looking at that and understanding that in more detail.
Yeah, I sort of like to think of it as, if we see multiple, it's the same way I like to think of how we might detect life on exoplanets, with multiple lines of converging evidence, converging on the same thing. I think what we want on Venus is, again, multiple lines of converging evidence. So some of that evidence might be on the surface, some of that evidence might be in the atmosphere. It all needs to point to the same thing and tell a story that we have to have past habitability to explain.
Yep, I agree with that.
Okay, we have two hands raised. Norm Sleep first, and then David Wilson.
Edward, go first. If not, I'll go. Can you hear me?
Yeah, Norm, hi.
Just a couple things here. It's a lot easier to get the Venus runaway if you have light. If you have an uninhabited Archean Earth where there are no platform carbonates, no banded iron formations, or very little, CO2 gets subducted into the mantle. When you go into the runaway, it's hard to get the 93 bars. You lose the water off the top. You end up with a dry planet in With the current lapse rate on Venus, if you just by fiat say take the bottom of it off, carbonates are stable at the surface, and then you're down to kinetics. If you have the large igneous provinces like Siberia, the CO2 is mainly coming from biology, from the buried coal, in that case, buried kerogen and sediment. So again, life helps. If you have the carbon stored in carbonate at the surface, when you run away, it gets metamorphosed as you go through the very high temperatures when the water gets out. Again, it gets very easy to get 93 bars of CO2. So there are other ways to do it. You can have the plate tectonics run after the runaway. And if you have, if you look at metamorphic rocks, I was trained as a geologist and never really practiced. But graphitic gneiss is obvious. Marbles from where the limestones have lost their CO2 are obvious. These rocks maintain their chemical integrity. You can even, if you go out and sample a mid-ocean ridge basalt, you can see the effect of subduction of organic material. Whether the not useful on Venus particularly, but you can see the fractionation of uranium isotopes from the oxygenation gradient in the slab, that the isotope that's deep in the ocean crust gets more easily subducted than the one that's at the surface. So I don't think it's hopeless. We have the fold belts on Venus. We know where they are. They're the past tense of black shales, past tense of platform carbonates. Look a lot better that there was life there in the past. And to explain it without life, I think somebody could do it, but it's like when you see a dead dog on the freeway, it's usually considered evidence of past life. Not quite that strong, but I am optimistic. You can certainly see the evidence of life on the Earth in mantle-derived rocks, and you could certainly see it in high-grade metamorphic rocks in the Earth's crust. So that's what you basically have on Venus because it's very hot.
Could carbonates survive to the present day on the surface of Venus?
That carbonate is, pure calcium oxide carbonate is stable. It's not stable in the presence of the salt, and also you have the acid there that you have to worry about, that it may form calcium sulfate instead. The sulfate somehow buffers the climate on Venus. The sulfur, there's a lot of sulfur in the atmosphere, but there's very little for any self-respecting basalt. So there has to be sulfur on the rocks on the surface and some kind of complicated buffer. The CO2 seems, my guess is it's unstable, that you get beyond the point where carbonate, you increase the pressure which stabilizes carbonates, but you also increase the lapse rate, the temperature at deck with the lapse rate, and increase the temperature always wins and destabilizes. So you have too little carbonates, but well, like 20 or 30 bars or so, depending on what the mineral assemblage is. They'll unstably go onto the surface except for kinetics. If you had a bar or so and it was a carbonate and it was dry, relatively dry, and water was cold trapped at the surface, you'd probably get the carbonates into the surface in a geological amount of time. It's complicated conditions we don't have on the Earth.
Okay, we've got another question.
Thinking about Venus again.
Thanks, Norm. I feel like I learn something every time I talk to you.
We have another question. David Wilson.
Yeah, so in the context of studying Venus as an exoplanet, what's for you the key missing information that we don't have about Venus that you'd like to see a future mission or future observations find out?
Well, I'm an astrobiologist, so I'm biased, but I want to know if Venus was ever habitable in the past. Because just knowing whether, if there were two worlds in our solar system side by side that were habitable, I think would help us to think about the distribution of potentially habitable real estate beyond our solar system. There was a recent study, and I feel so bad, I'm forgetting the first author's name, that was about Eta Earth, which is the fraction of Earth-like planets, fraction of stars with Earth-like planets. And they were suggesting that Eta Earth might be higher than previous estimates might have suspected, potentially as high as 80% of all stars having a potentially habitable planet around them. But that's only if you take an optimistic view of the habitable zone boundaries. This is how you get that 80%. If Venus was truly habitable in the past, that will inform how we might think about the boundaries of the habitable zone and the kinds of planets that might be able to support habitable conditions. So, like, for me, that's the holy grail. Certainly there's other things, better understanding the atmospheric composition is absolutely critical, because that will help us to that is critical input into our models, where we're going to be understanding the atmospheric composition of exoplanets. So one of the things that I mentioned, right, was this O2 question. And we don't understand where this O2 that we know is on Venus today, where it's going, because it seems to be disappearing from Venus's atmosphere very, very rapidly. So better inputs, to constrain our photochemical models that we're using to try to understand this very important question would be great. And that input would come in the form of better measurements of Venus's atmospheric composition, including the amount of ground state oxygen that's there. So yeah, those are some of the items on my wish list. There are other items, but for me personally, those are things that I want to know.
Any further questions for Giada? If not, I would like you all to join me in some way or rather showing your appreciation for this very wide-ranging and honestly fascinating talk. It was really great to think of Venus in a completely different way, as mysterious exoplanet-like thing that's very close to us, that has a totally unconstrained history with regard to habitability. So thank you very much, Giada.
Thanks for having me. I wish I could be there in person.